Hello viewers, I hope you are doing well. In this video, we shall be discussing few numerical problems concerning atomic structure, quantum mechanics, and molecular structure. This is part 2 of this series. We will discuss some important numerical problems. In this study, we will meticulously learn how to approach numerical problems. By solving a number of numerical based problems, we can easily memorize and understand various formulae and the underlying concepts. A student of chemistry is expected to remember numerical values and units of useful physical constants such as E, Me, Mp, Mn, Na, Rh, F, H, H cross, R, K, A0, etc. Also, the interconversion of various units should be learned. So we begin with the first question. Calculate the following parameters for Bohr's hydrogen atom. Radius of Bohr orbit, speed of electron in the Bohr circular orbit, frequency of revolution of electron in the first Bohr orbit, time period of revolution of electron in the first Bohr orbit, energy of electron in the nth orbit, Rydberg's Rh constant, and frequency of emission of radiation when electron jumps from n greater than 1 to n equal to 1 Bohr's orbit. Let us proceed. The first part, radius of Bohr orbit of hydrogen atom. Refer to figure 1 drawn over here. The circular orbit. At the center there is nucleus. Electron is orbiting. The radius of the orbit is r. Tangential velocity is u. The classical formula for radius of the nth orbit is given here. Rn equal to n square h square over 4 pi square z m square. In the SI system, this formula takes the form 4 pi epsilon multiplied by the above factor n square h square upon 4 pi square z m square. As we know, for hydrogen, atomic number z equal to 1. Therefore, the radius of first Bohr orbit, that is r1h, or Bohr radius E0, has been calculated over here by putting the values of various parameters, and the result comes out to be 52.9 picometer. Remember that this radius is according to Bohr's model, which is not perfect these days. Next, we proceed to calculate velocity u. The formula is nh upon 2 pi mr. So for the first orbit, u1 has been calculated by using the values of h, pi, m and r1. It comes out to be 2.188 into 10 to the power 6 meter per second. Third part, the formula for frequency of revolution. As we know, time period t equal to circumference divided by speed. Therefore, frequency equal to 1 over time equal to u over 2 pi a0. So f is, first we put the value of 1 over 3 multiplied by divided by circumference 2 pi a0. The formula becomes f equal to nh upon 4 pi square m a0 square. We put the values of various parameters and get the result 6.58 into 10 to the power 15 per second. Time period t per revolution 1 upon f. By putting the value we calculated for f, we get the result which is nearly 10 to the power minus 16 second. Now we proceed to calculate energy. The equation is En equal to negative 2 pi square z square m e power 4 over 4 pi epsilon square n square h square. If we put the values of different parameters, and remember that joule is kilogram meter square per second square, we derive E1 equal to minus 13.59 electron volt per atom. Various other units can be used. 1 electron volt means 1.6021 into 10 to the power minus 19 joule per molecule. So on molar scale, 1 electron volt equal to 96.48 kilojoule per mole, or 23.06 kilocalorie per mole. Another conversion is 1 electron volt is 8065.5 reciprocal centimeter. En calculation in general, En calculation can be done by the formula negative 1312.19 multiplied by Z square over N square in kilojoule per mole unit. For hydrogen, we have compared E2, E3, etc. with E1. The ratio is given here. Electron energy of electron increases with increasing n value. It means as electron occupies higher orbits, its removal from the atom becomes easier. Rydberg constant calculation. Rydberg constant is a collection of various constant terms, 2 pi square z square me power 4 over 4 pi epsilon square c h cube and n square. By putting values z equal to 1, n equal to 1, c equal to 3 into 10 to the power 10 centimeter per second and permittivity factor value, we get energy equal to, we get RH equal to 13.59 electron volt or 1,09,691 reciprocal centimeter. Correspondingly, energy of mth orbit is minus RH multiplied by Z square over N square. Now, Lyman series, calculation of energy in reciprocal centimeter of the first emission line in Lyman series of hydrogen spectrum. The formula is delta E equal over Hc, where delta E means E2 minus E1. So by using Rydberg constant, the equation becomes RH multiplied by 1 over N1 square minus 1 over N2 square, where RH value is given, and we get the result of Lyman series 32,268 reciprocal centimeter. Here I have given energy units. E in joule is Avogadro number multiplied by H multiplied by frequency. When you replace frequency by C over lambda, you divide delta E by H, you get frequency per second. You divide delta E by Hc, you get wave number reciprocal centimeter. So various units are used, and students should remember the significance of using various units because with different techniques use different units. For example, while dealing with infrared spectroscopy, we use wave number. While dealing with microwave spectroscopy, we use per second or wave number, both units. For energy, we use joule per mole unit. So students should be familiar how to convert one unit into other. We proceed to question number 2. Calculate the short and long wavelength limit of Lyman series in the spectrum of hydrogen. As we did earlier, frequency per centimeter is 1 over wavelength. equal to RH 1 over N1 square minus 1 over N2 square, where N1 is 1. For short wavelength limit, N2 is infinity. For long wavelength limit, N2 is 2. On calculation, we get lambda for short wavelength limit is 91.16 nanometer, and lambda long wavelength limit 0.1215 nanometer. Based on this formulation, many other numericals should be tried. Question number 3. Calculate ground state energy of electron in helium plus, lithium double positive, beryllium triple positive species using the formula En equal to minus RH Z square M square. We have calculated energy E1 for helium plus, lithium double plus, beryllium triple plus. A very interesting point is that ground state energy of hydrogen atom, which is 13.60 electron volt, is equal to the first excited state energy of helium plus ion, assuming that their Rydberg constants are equal. It is so because for the first excited state of helium plus ion, the multiplier factor is 4 over 4, because Z is 2, N is 2 for excited state. Question number 4. Show that R2 beryllium tripositive is equal to R1H equal to 5.29 into 10 to the power minus 20 minus 10 meter. The formula we used earlier, that is Rn square, Rn proportional to N square over Z. This formula can be used for calculation, and we find that the radius of first orbit of hydrogen is equal to radius of second orbit of tripositive beryllium ion. Hence proved. For the second, third, fourth, etc. orbits, the formulation is Rn equal to N square over N square multiplied by Bohr orbit radius. Rn equal to N square multiplied by Bohr radius A0. N is quantum number. For other hydrogen-like cases, Rn equal to N square multiplied by A0 divided by Z. Z is number of protons. Thus, R1H is comparable to R2 beryllium tripositive. Question 5. Why is Bohr's model of atom not in consonance with the Heisenberg uncertainty principle? We know Bohr's model was based on classical mechanics, which has no scope for uncertainty principle and probability theorem. Although the beginning of quantum mechanics can be traced back to Bohr's model of 1913, but what Bohr suggested is exact circular path of exact velocity, certainty. Heisenberg principle deviates from this concept. For many particles, very small particles, the theory of uncertainty is applicable. So for electron, we cannot measure energy and velocity and position simultaneously. There will be uncertainty. So in that respect, Bohr's model is not in consonance with Heisenberg's model. Question number 6. We need to derive de Broglie's equation. Very systematically it has been derived here. Einstein in 1905 suggested that energy of photon is mass into c square. Earlier, Planck suggested energy E equal to h nu. It means mc square equal to h nu, and nu frequency can be replaced by c by lambda. So h nu equal to hc by lambda equal to mc square. It means lambda equal to h upon mc. C is velocity of photon or particle. We can use the symbol u. Therefore, lambda equal to h upon mu or h upon p momentum. The wavelength of electron has been calculated and this small value can be measured. Hence, the de Broglie's wave particle duality concept stands validated. For large particles, the magnitude of wavelength is so small that it cannot be measured. Therefore, the de Broglie principle applies only for tiny particles, very, very small particles, not for large particles, not for microscopic particles. Question 7. Write the expression for the energy of interaction between an electron and the hydrogen nucleus, proton. How is this expression derived? We very often use this expression. VR equal to minus Jd square over 4 pi epsilon 0 r. In this video, we will learn how to derive this equation. When an electron, which is a point negative charge minus E, is brought from infinity, that is r equal to infinity, to the optimum distance, that is r equal to r1, a0, the work done is obtained using Coulomb law of force rule between the point positive charge of proton and electronic charge electron multiplied by displacement. So we can formulate the expression using the limit r equal to infinity to r equal to r, integral dvr equal to 1 upon 4 pi epsilon, integral z e upon r square dr. By rearranging and integrating, we get the result shown below. For bio students, it may be difficult to understand, therefore I have clarified it. Integration formula is shown below. 1 over 4 pi epsilon 0, because it is a constant taken outside of the integral. Integration z square r power minus 2 dr. Here z and e both are constant. They can be taken out. It means integral r power minus 2 dr. So it becomes r power minus 1 divided by minus 1. Collecting all these terms, the result becomes minus z square upon 4 pi epsilon r. The common rule is integration of a constant multiplied by variable x power n with respect to x gives k x power n plus 1 divided by n plus 1 plus constant of integration. Similarly, if the power is negative, again we use the formula shown here. Integration of k x power minus n dx equal to k x power minus n plus 1 divided by minus n plus 1 plus constant of integration. Question 8. Write the relation between Cartesian x, y, z coordinates and polar coordinates r, theta and phi for the hydrogen atom problem. With reference to figure 2, x equal to r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta. These can be proved by simple trigonometric relations. You see, 3 perpendicular axes have been shown as x, y, and z. Intercepts on each axis, x, y, z are also shown. The position of electron is marked P, x, y, z, and P are theta phi. The distance is r. The angle is theta on one side, phi on the other side. So we can derive these relations: x equal to r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta. These are very commonly used in quantum mechanics, so you should remember them. Now we are going to derive an expression for the kinetic energy of a diatomic rigid molecule, AB molecule, rotating about an axis perpendicular to the bond axis. Truly speaking, no molecule is rigid. Particularly at higher energy states, rigidity is not observed. But for ease of mathematical solution, we assume that diatomic molecule is rigid. It means its bond distance remains unaffected during rotation. So the rotation has been shown along the center of gravity, Cg. One atom is Ma, one atom is A of mass Ma, another atom is B of mass Mb. The bond distance is R, which is equal to R1 plus R2, as shown in the diagram. Now from the law of momentum conservation, MaR1 equal to MbR minus MbR1 by putting R2 equal to R minus R1. It means we can obtain the value of R1. Similarly, we can obtain the value of R2. And now we can write the expression for moment of inertia. I equal to Ma R1 square plus Mb R2 square. And finally, we derive I equal to mu R square, where mu is the reduced mass of AB molecule. Angular momentum L is given by I omega. I is moment of inertia, omega is angular velocity. Squaring L, it becomes I square, omega square. It becomes 2I multiplied by I omega square by half. Here I omega square by 2 is actually the kinetic rotational energy. So the expression becomes P rotation equal to L square over 2I equal to H square upon 8 pi square I J plus 1, where J is quantum number having integral values 0, 1, 2, 3, 4, etc. And quantum mechanical L is H cross under root J plus 1. On squaring, it becomes H square upon 4 pi square J plus 1. It means the kinetic energy is taken as total energy because if no external force is acting on the rotor, it means potential energy term is 0. So we have written the expression for kinetic energy. Ma V1 square by over 2, Mb V2 square over 2. Replace V1 by R omega. So we get the expression kinetic energy equal to L square over 2I. Quantized L value is given here. Therefore, kinetic energy term becomes H square upon 8 pi square I J plus 1. In frequency unit, we have to divide it by Hc. Note that the constant term H upon 8 pi square Ic is written as B, but for simplicity, for convenience, it is called rotational constant. Also note that Vj equal to frequency multiplied by Hc. Excitation of rotational energy states. For transition from J equal to 0 to J prime equal to 1, we get delta F to be in units of reciprocal centimeter. Thank you very much. I hope you have benefited from this video. A few more readings will be required before you can complete it.